Assalamu alaikum. Welcome to the thesis defense on decipherable classification of glaucoma using deep neural networks leveraging XAI. I am Anita Islam, 12th semester student of Computer Science and Engineering Department. I am profoundly grateful to everyone for joining today. Let's start. As we know, glaucoma is the second driving reason for partial or complete blindness among all the visual deficiencies, which mainly occurs because of excessive pressure in the eye due to anxiety or depression, which damages the optic nerve and creates complications in vision. In this research, we used the glaucoma dataset in our algorithm to predict outcomes related to glaucoma, suspicious glaucoma, and non-glaucoma. The main goal of this research was to develop an automated deep learning neural network architecture for early detection of glaucoma disease. We are going to use explainable AI to classify a scanned image of eyes that have glaucoma. XAI proposes the report to the decision of artificial intelligence, which means deep learning or black box to the extent that is human interpretable. However, it's one of the leading causes of blindness for people over the age of 60. Statistics show that even with the treatment, 15% to 20% of patients become blind. For this reason, in this research, we are going to apply explainable AI to detect glaucoma in an early stage in a better way than exists. The diagnosis of glaucoma is a complicated and expensive process, which is why it's important to detect as early as possible. The application of a deep neural network leveraging XAI can give more improvement in understanding or detecting many problems related to glaucoma disease. Well, since glaucoma is such a prominent reason for blindness around the world, we must apply our knowledge of classification techniques to classify the various types of glaucoma for the betterment of the world. We can easily use binary classifiers to differentiate between images of primary glaucoma and secondary glaucoma. And then we can use another binary classifier to differentiate between images of open-angle glaucoma and closed-angle glaucoma. In this study, we are going to use explainable AI to classify scanned images of eyes that have glaucoma. You must be curious about our proposed model and work plan, and this will be described by Tony. Thank you.
Hello, Assalamu alaikum. I am Anika Tuni, and now I am going to explain our proposed model and work plan. So, to classify the images of our dataset, we used black box classifiers. While black boxes are excellent for classification purposes, they do not provide any rationale behind their decisions. That's why we used explainable AI that extracts the features that are responsible for the decision. There are many XAI frameworks that explains the black box. We used one of the most popular Python XAI frameworks called LIME. For example, in the first image, the black box AI is only classifying glaucoma positive and negative cases. But in the second image, Lime is explaining the values of the features that were responsible for the outcome. We created the black box by feeding the inputs into a convolutional neural network CNN and then feeding the outputs of the CNN into a support vector machine SVM and into a fully connected neural network FCNN. These two are binary classifiers and they send their outputs to a softmax function which combines the decisions and provides the final verdict. Now I am going to explain our work plan. We split our dataset into training and testing dataset by ratio of 8:2. We pre-processed the data and extracted the features and trained our black box. Then we tested our black box output with the testing data. Simultaneously, we sent the output of the softmax function of line, and lastly, line visualizes the output to the user.
I am Iftikhar Rahman, and in this part I will be describing about the implementation, which is the fundamentals of deep learning and dataset, libraries and tools, and also the architecture of our proposed model. Before we dive into the topics, let's discuss about the fundamentals of deep learning. So what is deep learning? Deep learning is a type of machine learning and artificial intelligence that imitates the way humans gain certain types of knowledge. However, while traditional machine learning algorithms are linear, deep learning algorithms are stacked in a hierarchy of increasing complexity and abstraction. As our data are mostly direct fundus images from lake dataset, CNN is being used in this thesis for image classification, as it is a type of model which possesses data such as images. Also, it automatically understands low to high level patterns of image classification, which helps us to extract high representation of the image content. More of the dataset contains 4,250 images for training, 302 images for testing, and 302 images for validation. Here is a picture of a like dataset. The technologies which we use in this research is Google Colab and Jupyter Notebook for IDE, and the graphics card we used in this GTA X1660 Super OC. Moreover, we are using Python as a programming language, and some of the libraries we are using is TensorFlow, Keras, Matplotlib, Pandas, NumPy, and scikit-learning. In the study, a transfer learning approach is proposed. We have used fine-tuning approach of transfer learning. Here are the CNN models, which used in VG16, Inception V3, VGG19, ResNet 50, ResNet 1-to-1. Fine-tuning is the process of fine-tuning or changing a model that has already been trained for one task to make it execute a second related task. The architecture of convolutional neural network is basically three types of layers. One, convolution, second, pooling, and the third one is fully connected. And basically all these layers do this such operations such as convolution operation, pooling operation, flattening, nonlinear activation functions imply, and optimization operation. However, there are three types of pooling operation. One is max pooling operation, another is average pooling operation, and the third one is global average pooling 2D operation. Moreover, we have used batch normalization and dropout. So that's all from me. Thank you.
Assalamu alaikum. I am Tawhidul Islam Chan, and I am going to explain our paper's result and analysis part. First, we're going to look at the model's accuracy of each and every model. Every model was compiled in 50 epochs with the Adam optimizer with a learning rate of 1 to the power minus 1, which is 0.0067. And the best score we got from the ResNet 50 model with 94.7% of validation accuracy. Then chronologically, VG19 with 93.3%, then VG16, ResNet 1-to-1, and then Inception version 3. These are the accuracy and loss curve for each model. Red indicates trained and blue indicates for test. The shape and dynamics of a learning curve can be used to diagnose the behavior of a machine learning model. It also suggests the type of configuration changes that may be made to improve learning and performance. Smaller relative score on the y-axis indicates more or better learning, and by observing the models, VG19 had the best fit than others. And then there is ResNet 50, but the ResNet 1-to-1 is underfitted as the training loss is over the validation loss. VG16 and Inception version 3 got overfitted as the train loss curve goes under the value loss curve, or on the other hand, train accuracy is much more higher than the validation accuracy. Next, these are the true and predicted scores for classified and misclassified glaucoma and non-glaucoma results for each model. It is based on the model's training datasets, predictions level, and the actual train levels. We have added a threshold of 0.5 for the visualization, as our training score of ResNet 50 was 100%, so it showed no misclassified sample for this graph. Now we have called the same function that we have used for the above train predicted levels, again with the same threshold of 0.5, but for now we have used the validation datasets predictions. and the results were remarkably high for the ResNet 50 and DGG19. These are single and batch of 50 images predictions from our deep CNN models. Now we will show the explanation for these preprocessed and misclassified images using an AI framework called LIME. Then we will apply LIME again on a single predicted raw fundus image directly from the test dataset, which is already labeled to see the difference between a correctly predicted fundus image and a wrong predicted fundus image. From the previous misclassified images, we had undo the preprocess to show the difference between with preprocessed and without preprocessed images for each model. From this, we acknowledged that only the DenseNet turned the images into reddish and every other model did this kind of bluish. This red and blue contrast ruined most of the features or the image quality, which also might be the reason for wrong prediction. Here we can see the LIME explanation for each model's misclassified or wrong predicted images with their preprocessing input. The yellow area indicates the focused area for the models, which are the superpixels images given by the LIME. And below that we can see the superpixels and the explanation with the correct or wrong focused areas for the image for each model. Here the green part indicates true and red indicates false. These are the same kind of LIME explanations for the fundus images, except these are without overly contrasted pre-processing. Coming to the conclusion, we can say to attain the ultimate objective of our study in glaucoma detection, the black box model was defined using explainable artificial intelligence. Through this research, we are led to more glaucoma diagnosis acceptability. Notably, glaucoma can take away the vision of a patient, which is why it's more important to work with a better solution for early stage detection of glaucoma disease. To sum up, we can say this research has achieved the goal to bring more accuracy, reliability, and commitment to improving more in glaucoma diagnosis. I sincerely appreciate your attention. Thank you. Feel free to ask any question.